Welcome to ePathshala. I am K. Sangamitrai, Assistant Professor from the Department of Textiles and Clothing from Avinashliam Institute for Home Science and Higher Education for Women. Today we will be seeing on water repellent finishes and waterproof fabrics. We have come across these two terms, water repellent and waterproof fabrics, often, but we are not aware of the difference in these two terms. Today we will be seeing on the chemicals and the process used for preparation of these fabrics, that is water repellent and waterproof. By knowing these chemicals or the process involved, we may be able to select the suitable fabrics or textile material for the various end uses, so that we can obtain the maximum level of usability. Water repellent finishes. For a fabric to be water repellent, the critical surface tension of the fiber's surface must be lowered to about 24 to 30 dynes per centimeter. Pure water has a surface tension of 72 dynes per centimeter, so these values are sufficient for water repellency. This section will be devoted to describe materials that are used mainly as water repellent finishes. In the later section, we may be seeing of some of these combined with fluorochemical finishes to enhance both water and oil repellency. Oil repellency requires the fiber surface to be lowered to 13 dynes per centimeter. Only fluorochemicals are able to function as oil repellents, so whatever is mixed with them must not interfere with how they are deposited. The term waterproof is normally taken to represent the conditions where a textile material, that is treated or untreated, can prevent the absorption of water and also the penetration of water into its structure. Thus, a waterproof surface provides a barrier to water under all practical end-use conditions. In absolute terms, a waterproof fabric is fully resistant to penetration by water, implying that the fabric water penetration resistance is equivalent to its hydraulic bursting strength. However, in practice, a minimum performance of no penetration by water below a hydrostatic pressure of 100 centimeters is taken to represent a waterproof fabric. The major difference between water repellent and waterproof fabrics are in terms of pores, that is, the pores will be open in water repellent fabrics where it is filled in waterproof fabrics, and water vapor permeability where there are small to large in water repellent fabrics, whereas it is 0 to very small in waterproof fabrics. Air permeability is usually large in water repellent, whereas it is 0 to small in waterproof fabrics. And the resistance to water penetration, and here the resistance to water by rain drops and spreading and winking of water is permitted, whereas it is highly resistant under external hydrostatic pressure in waterproof fabrics. The most widely used method of producing a waterproof fabrics is by coating the fabric with a solid polymeric coating, for example neoprene, that is synthetic rubber, polyvinyl chloride or polyurethanes. Such coatings are not porous and therefore provide a continuous solid barrier to liquid water and other liquids such as oils. However, such solid non-porous continuous coatings are impermeable both to the passage of air and of water vapor. Such coated fabrics are therefore classed as waterproof but are not water vapor permeable, that is, they are not breathable. For many non-apparel end uses such as technical textiles, industrial fabrics, textiles destined for outdoor use such as tarpaulins or awnings, this does not create any problem. However, for high levels of comfort such as in apparel, a fabric in a garment must allow air and especially moisture, that is water vapor, generated by extrudation of perspiration from the skin during physical activity to pass through the fabric. This maintains the wearer of the garment in warm, dry conditions with high level of thermophysical and thermophysiological comfort. We will be seeing on fluorochemical repellent finishes. Fluorochemicals, that is fluorocarbons, are a class of synthetically produced organic chemicals that contain a perfluoroalkyl residue in which all the hydrogen atoms have been replaced by fluorine. Fluorochemicals exhibit outstanding chemical and thermal stability, low reactivity through their incompatibility with water and oil, and considerable reduction in surface tension. It is this later property which is of particular importance in the contents of water and oil repellency, while their chemical and thermal stability contribute towards the durability of the surface finish to fabric care treatments such as laundering, dry cleaning and tumble drying. Fluorochemicals are used in many fields, for example as durable lubricants, corrosion protection coatings for metals, flame retardant polymers, fluorine elastomers used in rubber industry and heat transfer fluids in refrigeration technology. They are widely used as protective agents against water and oil, stains and soiling in the textile, paper and leather industries. Some fluorochemicals are used for specialist wetting applications in the textile fleets. Others are used in firefighting and in electroplating and electronics industries. The first one under fluorochemicals is fluorochemicals finish formulations. The main components that may be present in typical fluorochemical dispersions are here. Oil repellency and water repellency depend crucially upon the perfluoroacrylate compound, but the presence of long chain fatty alcohol acrylates such as lauryl and stearin acrylate has been shown to produce synergistic improvement in water repellency with the perfluoroacrylate without adverse impairment of the oil repellency. Vinyl chloride, vinylidene chloride, methyl methacrylate and acrylonitrile are also frequently incorporated as commonomers where special performance characteristics are required such as oil repellency or resistance to organic solvents and white spirit. The major components of fluorocarbon dispersions includes oil repellency, then fatty acids, underwater repellency for use of fastness and white spirit repellency, etc. The fastness of the fluorochemical finish to domestic washing, laundering and dry cleaning can be achieved using reacting monomers such as acrylates containing methylo or epoxy functional groups. Such reactive functional groups may self-cross-link or alternately react with functional groups such as hydroxyl, amino or carboxylic groups in the fiber surface. The net result is that the fluorochemical polymers become cross-linked and is covalently bound to the fiber surface, greatly increasing the durability to domestic washing, laundering and dry cleaning. A softer handle can be attained by the incorporation of high molecular weight polydimethylsiloxanes. The oil repellency can be enhanced by the use of fluorinated urethane structures, and the precise structure of the urethane components used can be varied within wide limits in order to optimize the performance capabilities of fluorochemical finish to suit the end use requirements. The aqueous fluorochemical emulsion or dispersion must be stabilized using an appropriate emulsifier. Fatty alcohol ethoxylates are used as non-ionic emulsifiers and quaternary ammonium salts used as cationic emulsifiers. Anionic surfactants are also used, but in practice it has been found that the combinations of several surfactants provide more stable emulsions, and hence this approach is widely utilized. The choice of emulsifier is critical because it has a considerable impact on the overall performance of the fluorochemical formulation. In processing, the emulsifier system used must provide a formulation that exhibits acceptable manufacturing characteristics allied with satisfactory shelf life and transportation properties. In terms of application of fluorochemical formulations to textile materials, the diluted emulsion must be stable under the application conditions. This means that the diluted emulsion must be robust to changes in pH, temperature, pad speed, shear resistance and pumping conditions. Other auxiliaries used along with fluorochemical finish formulations include solvents, regulators and initiators. The solvent is essential for synthesizing the emulsion and also assist in the film forming process. Regulators are used to decrease the molecular weight obtained from free radical acrylate polymerization, which itself is catalyzed by initiators based upon azo or peroxide compounds. The second one is water repellent finishes other than fluorocarbons. Under this, first one is metal salt finishes. In the period from 1880 onwards, when water repellent finishing became more important, it was normal practice to impart water repellency by tightly woven cotton canvas by lengthy impregmentation, that is from 24 to 48 hours in an aluminum acetate solution at 5 to 9 degree Thwandal. Thwandal is a degrees in measure of specific gravity. Alternatively, water repellency was achieved by a zig or pad application of such an aluminum acetate solution, followed by careful drying in festoon form or on a stenter. To avoid precipitation of insoluble basic acetates, the impregmentation liquid temperature was maintained below 38 degrees centigrade. During drying, the removal of water was accompanied by removal of some acetic acid, which then converted the water soluble monobasic salt into an insoluble dibasic compound. The latter was precipitated onto the fibers to give a water repellent finish with a harsh handle and with a very limited durability to washing. The second one is soap. One method of improving the water repellency obtained through the use of aluminum salt is by combining the aluminum salt treatment with treatment in soap in order to deposit insoluble hydrophobic aluminum soap within the fabric. Alternative procedures were developed to achieve satisfactory result. In one treatment, cotton fabric was first impregmented in 5 to 9 degree Thwandal, aluminum acetate squeezed and dried or partially dried. It was then passed through a weak aluminum sulfate solution. This later stage ensured that the maximum water repellency was developed because any soluble sodium soap remaining in the fabric was then converted into the water insoluble aluminum soap. The fabric could then be rinsed in soft or hard water and dried. Alternatively, 2 to 5% soap solutions at 60 degrees centigrade was padded onto the fabric, which was then partially dried. The third one is wax finishes. A popular form of water repellent treatment over the 20th century and still used today is the application of wax treatments to fabrics at open width. Many patents have been issued on the application of fats and waxes. Typically, wax formulations contain paraffin wax, either by itself or in combination with one or more waxes based upon esters of higher fatty acids and higher monohydric alcohols. Beeswax, carnauba wax and Vaseline have also been used according to the finisher's requirements. The fourth one is pyridium based water repellent finishes. In 1931, research work by Dutch Heidrijk led to patents on the manufacture of quaternary ammonium salt with the objective of giving an increased dyeing effect on cotton and cellulosic fibers. Typically, halogen esters of the general formula was reacted with tertiary bases to yield water-soluble quaternary ammonium compounds. Thus, the reaction of octodecanol formaldehyde and dihydrochloric could yield a substituted methyl chloride through the reaction. This could then be further reacted with tertiary bases such as triethylamine or pyridine to generate quaternary ammonium compounds with good aqueous solubility and strong wetting out and forming properties. The fifth one is organometallic complexes. Both chromium and aluminum organometallic complexes have been used to impart a semi-durable water repellency to textiles composed of either natural or synthetic fibers. Quilon, that is DuPont, was marketed as a concentrated solution of Werner type chromium compound in isopropanol and applied by a pad dry cure method. The Quilon chrome complexes produced fabrics with a soft handle and with a high initial water repellency, but their more widespread application was greatly restricted because of the blue-green coloration that was imparted to the fabric. The main textile end users were therefore restricted to tents, awnings, boat covers and surgical drapes and gowns made from non-woven materials. Similar products were marketed by a number of manufacturers. For example, Phobodex CR, that is Ciba, Cutolon W and Ombrophobe, while Quilon chrome complexes were still manufactured. The main applications now lie in materials other than textiles such as paper, packaging, release films and leather. The next one is methylol derivatives. The introduction of N-methylol compounds as self-cross-linking resins and of cyclic reactants that can form cross-links with functional groups in fibers gave rise to a new method of water repellent finishing, namely the use of resin wax emulsions or dispersion. A large number of patents have been issued in this field since 1930s, largely because this route opened up the possibility of producing wax-based water repellent finishes that were durable to high temperature washing. As a result, a large number of waxy and long-chain fatty acid type compounds have been reacted with various N-methylol based derivatives in order to produce water repellent finishes with greater durability that may also be incorporated as extenders for fluorochemical finishing. The next one is the silicon finishes. It was 50 years after the discovery of tetra-substituted asymmetric silicon compounds by Kipling and his co-workers in 1901 that silicons based upon polysiloxanes were first used as textile water repellents in UK. The hydrophobicity of silicons was first discovered by Padnod, who noted that paper treated with chloromethylsilanes was water repellent after exposure to moist air. Water hydrolysis chloromethylsilanes to silanols, which then condense spontaneously to form siloxanes. Polysiloxanes are based upon with an OSI-OSI backbone where or may be a hydrogen, hydroxyl, alkyl, aryl or alkoxyl group. Polysiloxanes for use as water repellent agents for textile are usually mixtures of linear polydimethylsiloxanes and polymethyl hydrogen siloxanes. Now we will see the other novel treatments with potential for water, oil, soil and stain repellency. The first one is the lotus effect, biomimetic ultraphobic surfaces. Biomimetic mimics naturally occurring biological mechanism with modification to produce useful imitative synthetic items using conventional methods available to science and technology. The lotus effect has been named after the unusual properties of the leaf surfaces of the lotus plant, which are remarkably water repellent and soil repellent. The surface of the lotus leaf is covered by a thin extracuticellular membrane termed the cuticle, which is covered by waxes forming characteristic microstructures due to self-organization. On smooth wax layers, that is surface area contact at 10%, the contact angle of water may reach 110 degree, but because of the surface roughness of the wax layer, whose dimensions can be measured in micrometers, a very pronounced superhydrophobicity is generated with contact angles up to 170 degree and surface area contact as low as 7%. As a result, the area for adhesion of water is markedly diminished and air is enclosed between the droplets and the wax crystals. The second one is pulsed plasma polymerization of monomers. Conventional fluorochemical based water repellents are produced using combinations of resins, catalysts, homo and copolymers, surfactants, pH adjusters, cross-linking agents, heat and solvents. It has been pointed out that such process can consume large amounts of solvents, are costly, produce large amounts of waste and are highly substrate dependent. The method of pulsed plasma polymerization of monomers containing long perfluoroalkyl chains linked to a polymerizable carbon-carbon double bond avoids the need for using solvents. Deposited films can exhibit super repellency whereby liquid droplets just roll off the surface. This phenomena of super repellency is in part dependent upon the length of perfluoroalkyl chains. The third one is plasma treatments. Plasma treatment of textile fibers and other forms of textile material in fluorocarbon gases or gas mixtures have been studied in the research laboratory and by suitable adjustment of the process parameters, non-wettable, highly hydrophobic surfaces can be achieved on polyester textiles. The chemical surface modification and the surface roughness have been demonstrated to be responsible for the non-wetting properties of the treated fiber surfaces, and the low energy polymer surface treatment also acts as a diffusion barrier for protecting the bulk material against chemical attack. The next one is with the treatment with reactive fluorinated compound in supercritical fluid carbon dioxide. Research studies have shown that low molecular weight reactive fluorinated compounds can be made to react with fibers in a polymer analogous way. Thus, it is possible to create a well-oriented, very thin layer composed of CF3 groups. The close packing of the CF3 groups ensures that there is a decreased tendency of reorientation in the presence of polar interfaces. Therefore, the repellent effect persists under water. The fifth one is coating textiles with organically modified ceramics. At present, this technique is still in the development stage, but it is conceivable that it could prove to have potential within the textile industry. In this novel approach, the precursors, that is metal alcohoids and organically modified metal alkoxides, are converted into stable colloidal solutions by partial hydrolysis. The coating of this colloidal solution onto the textile may be carried out by the conventional techniques such as dipping, spraying or padding. Treatment of the salt is then carried out using UV radiation, thermal treatment or by evaporation of the solvent, which leads to condensation reactions and agglomerations, causing the salt to gelate and form transparent layers. The last we will be seeing on the test methods used for testing the water repellency. There are three main types of test methods used to evaluate the water repellency of the fabrics, which should be suitably preconditioned prior to testing under standardized conditions. The class 1 is spray test to simulate exposure to rain. Class 2 is hydrostatic pressure test. These measures the water penetration as a function of pressure exerted by water standing on the fabric. Class 3, absorption of water by the fabric immersed in water. The most widely used test methods is a test where the test specimen preconditioned at 65 plus or minus 2 degree relative humidity and 21 plus or minus 1 degree centigrade for at least 4 hours prior to testing is backed by a weighted blotter and is sprayed with water in the H09TC rain tester for 5 minutes under controlled conditions. The severity of the simulated rain is altered by changing the height of the water column to give pressure of 60 to 240 centimeter water gauge. The blotter is then reweighed to determine the amount of water that leaked through the specimen during the test. The fabric performance is given by determining the maximum pressure at which no fabric penetration occurs. The change in fabric penetration as pressure is increased and break down the minimum pressure required to cause a penetration of more than 5 grams of water. Class 2 hydrostatic pressure test. For many high performance fabrics that are rendered waterproof, a hydrostatic pressure test may be conducted in one of two ways. First one is by subjecting the fabric to an increasing hydrostatic pressure and measuring the pressure required to cause penetration. The second one is by subjecting the fabric to constant hydrostatic pressure for a long period of time and noting whether any penetration occurs. In class 3, absorption of water by the fabric immersion in water test, H09TC test method 70 was followed. Water repellency tumble jar dynamic absorption test. This test method measures the absorption of water into fabrics which may or may not have been given a water resistant or water repellent finish under dynamic conditions similar to those often encountered during actual use. Preconditioned and pre-weighed specimens are tumbled in water for a fixed period of time and then are reweighed after the excess water has been removed by a Wringer method. The percentage weight increases of the specimen is taken as a measure of absorption or resistance to internal wetting. We now looked upon the various water repellent and waterproof fabrics or the treatments, the chemicals used in the finishing given to fabrics. By knowing the various chemical compounds or the process at varied temperatures and methods used, we will be able to select a suitable method to apply on fabric surfaces to produce a water repellent or waterproof fabrics. By doing so, we may be able to obtain the suitable fabrics maybe used for maybe domestic purpose or even for industrial applications. By doing so, we may be able to obtain the maximum usability of those textiles with full potential. Thank you.